Hi everyone, we are from Group 3. I'm Wu Chao-ing.
I'm Chang Kai.
I'm Sarajan.
Okay, so today we are going to have a summary of all the phases we have done in ESP. So at first, the first phase, we have downloaded 4 ECG signals from e-learning and we are going to import them into the Scilab. Okay, so we have write the coding to show the signals, and all these signals is in time domain. Okay. We have typed these 3 coding to show the title and label the x and y axis. We also use subplots in order for the signal to show in one window.
As you can see, here is the 4 ECG signal that reported, and the sampling frequency for ECG1 is 1000 Hz, ECG2 200 Hz, ECG3 50 Hz, and ECG4 10 Hz. From the signal plotted, we can see that the higher the sampling frequency, the clearer the signals are. The sampling frequency must be at least the Nyquist frequency of the signal, which is twice the frequency of the signal. As we know that the hardware has noise of 50 Hz, thus we need a sample that can clearly show the noise so that the signal will not be distorted after filter. Therefore, the best signal would be ECG1 from our observation. And after that, we are given a signal which is distorted by a noise and a difference equation of a filter in part 2. With manual calculation, we get the impulse response by converting the difference equation. We change it into impulse response and convert it with the distorted signal manually and through Scilab.
So now come to the second part of the phase 1. So now we are given the xn function here, and we have done it by simulation in Scilab, and we have done it by manual calculation here. So the n is started from 0 to 20, and the function is here, and we have plotted it in discrete form. And we also verified the whole manual calculation with the simulation in the Scilab. So we are using the same coding, n is started from 0 to 20, and you can see the x result here is exactly the same as the result here. So after that, we are given one more equation here, xs. The xs is the one more signal introduced in the xs. So the result is here. You can compare this, it's exactly the same. And for the graph, it's also the same as the manual calculation that we had, based on the manual calculation that we have done. So for the Hn, we are given the difference equations, so we convert it to the impulse response, and this is the result that we get: 0.1, 0, and 0.1. It's 0.5, 0, and 0.5. So we also done it by manual calculation, and the graph is here. It's exactly the same. And lastly, we have convoluted the filter, the impulse response of the filter with the XSN, which has the noise. So the result is here. You can see that the graph is like this. It's exactly the same, and the data is here. Yes, the data is here. So our result is verified by the Scilab.
In phase 2, we are required to discuss 3 topics in the forum, and the first one will be how to plot pole zero plots using the filters given in phase 1 part 2. And the second will be how to plot the spectrum for all the ECG signals and the filters in phase 1 using Scilab. The third one will be the observations and analysis of all the plots. In question 1, we are required to plot a pole zero plots for the filter in phase 1. So we have use the impulse response that we got from phase 1 and we have converted it into the system functions by using Z transform. We have typed the codings here, and we are using the codes of PLZRs to plot the whole zero plots directly. And this is the plot. For the 0 is represented by circles, so there is 2 circles here, so means 2 zeros. And the poles is represented by an x, there's 2 x here, so there is 2 poles in this system.
Okay, so for the second questions, we are required to use the signal from the phase 1 to plot it in frequency domains. So firstly, we are plotting the ECG 1, 2, 3, and 4 in the Fourier transform. So we are using the FFT. Actually, this is the fast version of the discrete Fourier transform. And after the Fourier transform is done, so we are using the ABS, which is means by the absolute value of the FFT that have been done. So we plot it. You can see that this is the ECG 1, 2, 3, 4. And the value on the horizontal axis is actually K, because the DFT is a sample versions of the Fourier transform, so it's sampled in 10,000 samples, and this one is 2,000 samples, 500 and 1000 samples. So this is the discrete Fourier transform for the ECG signals. And for the second part, the xn, xsn, hn, and lastly the yn. So we are using the signal from the phase 1. Actually, we have only added the FFT functions and the absolute value, and we plot it. So this is also the discrete Fourier transform for these 4 signals. And you can see that after the noise is added to the xn, there is an amplitude at the k equal to 5. So after the filter is filtering out the X signal at k equal to 5, so you can see that the Y can obtain the original signal from the same as the xn.
For the topic, we need to observe and analyze all the above plots. For the pole-zero plot, we can conclude that the system is stable as all the poles are lying within the unit circle. On top of that, the system is causal as there is no value of in Hn for n less than 0, and the RC is an outward type. For the signal and filter from phase 1 part 2, the spectrum of input signal Xn display one sharp peak and another one mirror. And then for however, the input signal which is distorted with the noise Xsn has 2 additional sharp peaks as shown here. These additional 2 sharp peaks represent the noise signal which distorted the Xn signal. And then the output Yn signal is the product of convolution between Xsn and Hn. The output signal show the effect of filter where you can see the additional 2 sharp peaks has disappeared and it becomes a small semicircle right here, and the amplitude is greatly reduced. Convolution with filter brings the value of each pixel into closer harmony with the value of its neighbors. It is also called smoothing operation. Hence, the effect of noise can be reduced.
In this topic, we are going to verify the stability and the causality of the filter by varying the K value of the filter. So this is the system functions of the filter. So it has 2 zeros and 2 poles here. When we increase the K value equal to 5, so we can get the 5 poles and 5 zeros. When the K is 10, there's 10 zeros and 10 poles. And K is equals to 12. You can notice that there's 12 poles and 12 zeros. So this does not affect the stability and causality of the filter at all because the pole is always within the unit cycle. So the system will always be stable when K value is varied.
In phase 3, we require to design a filter to remove the noise corrupting the ECG1 signal in phase 1. So we are using low-pass Butterworth filter. The reason we use it is because Butterworth filter will produce a maximally flat response with no ripples and pass band from 0 Hz until the cut-off frequency. As we are using the low-pass second-order Butterworth filter, higher frequency beyond the cut-off point will roll off down to 0 in stop band at a rate of 40 dB per decade. We are not using first-order filter in this case because the shape or width of roll-off will be too long and wide. It is not efficient to eliminate the noise signal. We are using low-pass filter because the noise in the signal is 50 Hz, which is higher than the frequency of ECG signal, which is normally lower than 10. So we are using a filter type of IIR, which is infinite impulse response, and we are using the cutoff frequency of 40 Hz.
So we have designed a filters to remove the noise in ECG1s, and this is the specifications of the filter. We are using second order filters, and the sampling frequency is 1000 Hz. It follows the sampling frequency of ECG1s. The cutoff frequency is 40 Hz as the noise signal is 50 Hz, so we are using a frequency which is slightly lesser than 50 Hz. And for this, IIR is used, so we type here IIR. LP shows that it is a low pass filter. BUTT shows that it is a Butterworth filter. F cutoff divided by Fs divided by 2, this is actually the cutoff frequencies of these filters. Since we are using low pass of cutoff frequencies, so we only have one variable here. We put a 0 here. And for this one is actually the ripple vectors of the filter. Since we are using Butterworth, it will be no ripple for the filter, so we let it to be 0. TF to SS is to convert the system distracted by transfer functions to system distracted by state space representations. FLPS is to show the filterings of signal by linear systems. So the ECG ones if the ECG signals with noise, and SL is the filter. So now we are going to plot the ECG ones and the ECG ones after filters in time domains. So we have written it in these codings, and it will show the filters ones and the one without filters. And we also do the codings for the frequencies domains. So everything is remain the same, just that we have add some codings, which is this one. The FFT is to perform the fast Fourier transform and to display the waveform in frequencies domains. And ABS is the absolute value of elements in ECG1 frequencies. So it is a complex modulus of ECG1's frequencies if ECG1 is a complex number.
We show the discrete Fourier transform for the original ECG1 signal, and we show the filtered ECG1 signal as well. So now we change the discrete Fourier transform into Fourier transform, which means that the horizontal axis will become the frequency instead of the K. So the code is typed below. The signal length based on the ECG1 is 10,000, and we divide the length into 2, and we find the hash axis INC is actually the scale of the horizontal axis. So the Fs is actually 1000, and so 1000 divided by 2 will be 500, and divided by 5000 again, so the scale will become 0.1 Hz. So the x-axis, it will start from 0 with a scale of 0.1, and it will end until the 500 minus 0.1, because to shift the graph from 0.1 to 0. So actually the discrete Fourier transform, it will start from 0.1, but now it will start from 0. So we have plotted with the axis here, and the magnitude multiplied with the 1 from 1 to the 5000s. So these two graphs is to show the DFT for the ECG1, while this one is the FT. So you can see that actually before the ECG1 is filtered, the noise frequency is 50 Hz here. So once it's filtered, there's no more frequency on the 50 Hz. So which means that the ECG1 is actually successfully filtered by the IIR filter design.
In time domain, you can see that this is the original signal of ECG1. This is ECG1 after filter. So we can see that all the ripple embedded to the signal is being filtered out. The signal becomes very smooth. And this is because it shows that the Butterworth filter effectively removes high frequency noise from the distorted ECG signal.